yesterday we were talking about like some uses of parabolas. So we only got through the headlight, right? What are some other uses? What are you doing, Derek? All right, Derek, go sit down. All right. I'll bet just about every single one of you has a satellite dish that they use at home every day. How does a satellite dish work? Huh? All right, so
there's a transmission point that bounces off the satellite orbit and goes to the satellite location.
well, that's the general idea of how it works. Like there's satellites up in space, guys, and they're sending down these radio waves, right? And these radio waves, guys, these radio waves are all moving in parallel lines, okay? Guys. Now, the way the satellite dish works, what part of a satellite dish actually has like electronics in it that can collect like all those radio waves? The only part is that point, right? And actually that receiver, guys, that receiver is actually pointed back at your house. Meaning that radio wave that's coming in and hits the receiver directly, it can't actually receive that data. Like it's kind of blocked. It hits it in the back. It can't actually receive that information. The way a satellite dish works is every single, just like the headlight, every single wave that hits the satellite dish, where does it get bounced to? It gets bounced directly to that focus point, right? So basically all the satellite dish parabola is doing is collecting more radio waves. The bigger the parabola, the bigger the dish. What's the only thing that's really it's going to do? It's going to collect more waves, right? It's going to be a stronger signal. It's going to magnify that signal even more. So all it's doing is it's magnifying all of those and it's collecting more. Does that make sense? Now, if this is your satellite dish, right, is this distance important to know? Why? What's happening with all these radio waves? Bound to this point, right? If that receiver was a little bit too far away or a little bit too close, what would actually happen? It would completely miss all of those waves, and not only would it be less effective, it actually wouldn't work at all. Because now, if that receiver was a little bit too far, it's not going to collect any information. So knowing that distance is critically important in order for satellite dishes to work. And every parabola is a little bit different, so depending on how it's made, that distance has to be able to be calculated. And there's times in math, in real life, where experimental, where you just kind of build something, kind of guess and check, and you just kind of play with it until it works better, is a good idea. But there's also a time and place where doing things mathematical, where you actually calculate how big that distance should be, and it becomes a much easier way to do that. This idea of magnification is actually becoming a really popular way of doing solar panels, where you put a bunch of solar panels on your house and they're all those rectangular ones. The problem with those is they take up a ton of space, right? And each one of those panels is fairly expensive to build. Well, what they're doing now is they're creating basically satellite dishes where the parabola is just a giant mirror. Where's the only solar panel that has to collect the sunlight? Where does that have to be? Now you only need one of those, and you put it right at the focus point. Now, if you use this for solar, what's going to happen to that point right there? It's going to get hot. It's going to get real hot. So that one solar panel has to be able to withstand like an immense amount of energy. But now I only need one panel instead of thousands of panels. So it actually becomes cost effective. There's actually, stop following me. There you go. There's actually a toy that I really want to buy. So if someone wants to buy this for me, feel free anytime. This is something I've always wanted to buy for taking camping. Okay. Yeah. So they make these, it's called a solar grill. And basically, it looks like a giant satellite dish. And you point it at the sun, and basically, what ends up happening is, you know, you put your frying pan at the focus point, and you can cook steaks real easy.
Do you know that illusion trick that they always show us in like the 7th grade? There's one just like that, to where it's also a solar cooker, to where the energy's focused through the top, and it all reflects on whatever you have in it. And the way that you watch to see if it's cooking is it actually projects the hologram of whatever you're doing.
That's really cool. Another thing that is I've always wanted to do, and you know, my budget's not, you know, exactly a high budget these days. So if you ever get a chance to go to NC State, North Carolina State University, they built one out in their courtyard. There's a couple. It looks like art, and basically what it looks like is two giant concrete blocks. They're just these two huge blocks, okay, and they're facing each other. And the concrete blocks themselves are they're like 100 yards away from each other. They're actually really far. It's basically like the equivalent from here to the parking lot, away from each other, okay? And they're just these two concrete blocks. They're like 8 to 10 feet tall, maybe a couple feet. They're just these huge concrete blocks, and people just look at them, they think they're perfect. But in each concrete block, what they did was they hollowed out a parabolic dish out of each one, and they're facing each other. Okay? So there's these two parabolic dishes inside of these, right? So there's like a hole carved out. And then in each one, there's a seat that you can sit on. Okay? Now, if you sit on one and you have a friend sit on the other, you can talk to each other.
No.
Absolutely. Because when sound leaves your voice, what direction does it travel? It goes in every direction, right? Most of it is projected forward, right? But it goes in all directions. It works better if you're facing into the parabola and you're actually facing away from your friend, so you're, you know, looking away from each other. But what ends up happening is all those sound waves that leave your mouth, they get focused, or they get reflected, and every single one is reflected in a straight line out. Now, if you're standing here, would you be able to hear that person? Not really, because all those sound waves are mostly just going to miss you. Yeah, you might be able to hear them a little bit, you know, because it will get magnified to a point, and you'll collect some of those as they hit your ears. But what ends up happening is all those sound waves get reflected to the satellite dish, and then where do they get refocused? They get refocused right at the focus point that your friend is sitting at, and they actually do work. So I've never been there. I've just seen reports, and I've seen people talking about them. It's at NC State. They did it there. So if you're walking around their campus, it's on NC State University. They built one, and supposedly they work really well. Yes? I'd love to take a field trip, but
There's actually
about 100 yards.
phenomenon that actually works similar to this.
And I'm going to talk about that later.
The The center of Earth.
What's
Or is that what you're talking about?
Center of Earth?
It's really, it sits on the equator, and there's this one inner circle and an outer circle. People who are in the outer circle can't hear anything from the inner circle, even though they're literally 2 feet away.
Yeah, there's
People on the inside can talk, but they can hear anything from the outside. They don't know how it happens, but it's...
there's a phenomenon like with concerts where if you pay attention to how concerts are set up, they'll strategically place their sound engineer, and this is generally true in only big, like real acoustic centers. Not like if you go to a concert at Ford Field, it's just a giant. It's not designed for that. If you go to more of a what are those called? Huh? Is that no amphitheater? If you go to like an amphitheater, you'll see like this might be the stage. There'll be a spot like directly out in the middle of the crowd where the sound engineer will sit. And the reason is when they put their giant speakers here, the way the sound always gets deflected, it always mostly will miss that spot. So there's actually like a quiet spot, so they can hear the sound of how it's actually being presented to the crowd, and it's not like reflected, and because every time it gets reflected, it gets changed just a little bit. The volume and the pitch gets tweaked. So they have the absolute optimum sound area. That has nothing to do with the parabolas that we're talking about, but I think that's more along the lines of what you're talking about. It's kind of that same phenomenon of how that happens. But anywho, is there a time and place where it's really important that you actually would want to mathematically be able to calculate the focus point and be able to find that versus just building a parabola and guessing and checking? And the answer is yeah, it really would be more beneficial to mathematically calculate it versus just guessing and checking. Just take example, the NC State example. Do you think building those two things was cheap? Like, that's a lot of concrete, and concrete's pretty expensive. I mean, that's basically what they built them out of. You probably could build it out of something else, but, concrete's probably the easiest thing to build a big form and fill it so it actually works with the shape. The problem is, why would I want to mathematically calculate where the focus point would be? Well, number one, it's not going to work. Number two, the focus point might end up being like 10 feet out in front, where you have this big shape, but the focus point is actually way out here. Maybe that's not what you want. Or maybe the focus point is only 6 inches from the back of the parabola. Well, that's not going to work either, because you'd have to be so far in the parabola where you'd have to climb inside, kind of thing. So you want to be able to mathematically predict where it's supposed to be. Does that make sense? All right. So how do parabolas work? They're actually really easy. This you might want to write down. There are 2 standard equations for parabolas. There are 2 because direction matters. We're going to have a parabola, or we're going to have one equation for parabolas that go up or down, and we're going to have one equation for when parabolas go right or left. Okay? Standard equations are this. Before I do the standard equation, okay. All parabolas have a few important characteristics. 1, the focus point. 2, a vertex. Now, right now, where is all of our vertexes going to be? 0, 0. So I'm not going to ask you to find the vertex right now. Eventually I will, but not right now. And then they all also have what are called directrix lines. Now, the actual definition of a parabola is every single point on this parabola, no matter where you are, if you measure the distance, I'll call that D1, the distance from that point to the focus point, and the distance that is away from the directrix line, those two distances will always be equal. That's what actually makes parabolas. Okay? When those two distances remain constant, and as you move along, you take this point and you measure that distance and that distance, those will be the same. So what do you think is true about the distance from the vertex to the focus point and the vertex to the directrix? They're also going to be the same. Okay? Easy enough? Good job. That means I'm a good teacher if you can just pick up on stuff like that. Yeah. Okay. So we're going to have two standard equations. We're going to say the focus point is going to be at point P. Okay? Both of these would be at P. Okay? That also means we're going to have a directrix line back here at negative P. Okay? Now, yes, I'm going to ask you to find equations of lines. You do need to understand, is it a vertical line or a horizontal line? If it's a horizontal line, would it be a y equals negative p or an x equals negative p? Think about the equation of a line. This would be y equals negative p. This would be x equals negative p, because all horizontal lines are y equals, all vertical lines are x equals, right? I'm also going to ask you not to just label when you label things as points. I don't want you to just label it like this. I would actually want you to label that as the point 0p. And then this would be the point P0. Why do I want you to do that? Because there's a difference between 0p and P0. That helps me understand that you understand, is this parabola going up or is it going to the right? The two standard equations are this. If you see a parabola going up or down, it'll be x squared equals 4py. That's standard equation. I know, I've noticed. If it's if it's right or left, it'll be y squared equals 4px. Those are your two standard equations. So here's how easy this is. For example, I'm going to give you something like this. X squared equals 20y. Your job is to graph it and label all the important characteristics. If x squared equals 20y, if I compare this with the standard equation, what has to be true about that part and this part of the equations? They would have to be equal. So I can just say 4p would have to equal 20, so p is going to equal 5. Simple enough? I can tell everything I need right now. What direction is this parabola going to go? Well, if x is squared, that means the parabola has to go either up or down. If p is positive, which way do you think it's going to go? It's going to go up. So I'd go 1, 2, 3, 4, 5. My focus point is going to be at 0, 5. I'm going to go down 1, 2, 3, 4, 5. I'm going to draw my directrix line. And that's a horizontal line, so that would be y equals negative 5. There's the equation of my directrix line. And then I can draw my parabola. Parabolas kind of work similar to circles, meaning hold onto the string and walk in a circle. He's going to walk in a pretty tight circle. If I do the same thing to Owen in the back of the room, and I give him a string and say walk in a circle, he's going to walk in a much fatter circle, right? The bigger the p-value, what do you think happens to the parabola? The more it widens out and gets fat. Okay? The smaller the p-value, the more it narrows down. The way I'm going to have you guys graph these is not precise. I don't want you to like plot a bunch of points and get real precision. Basically, I'm looking for fat, medium, or skinny. If you see a p-value of basically less than 1, what I want you to draw is a skinny parabola. You see like a quarter, a fifth, something like that. If you see a p-value basically, well, I'll even say less than that. Less than maybe, I'll say 3/4. You draw something skinny. If you see a p-value somewhere between 3/4 and maybe like 2, basically right around 1, you're going to draw a normal looking parabola. If you see a p-value greater than, say, 2 or 3, all I want you to draw is a fat parabola. You're going to go skinny, medium, fat. And I don't have a better way to describe that other than skinny and fat. I mean, just narrow, wide. Easy enough? That's really all it is. So if I give you something like y squared equals negative 8x, what direction is this parabola going to go? Up, down, right, or left? If y is squared, that means it has to go either right or left. When I go 4p is going to end up equaling negative 8, so p is going to be negative 2. Do you think this is going to go right or left? It's going to go left. So I'd go left 2. There's my focus point at negative 2, 0. I'd go right 2. There's my directrix line at, now it's a vertical line. All vertical lines are x equals 2 now, right? And then this one, I would draw a fairly normal looking parabola going left. Yes?
If it's y squared equals negative 8x, is there like imaginary numbers in there somewhere?
What he's talking about is taking the square root of negatives, and no, there isn't imaginary numbers in there. That's actually why the parabola doesn't go over here. Because if I were to put an x value of, say, 2 in, 2 times negative 8 would be negative 16. Well, I can't solve and take the square root of negative 16. That's why there's no points over here, right? The reason it's actually a parabola and not just this part of this u, let's say you plug in a negative 2. What's negative 8 times a negative 2? Positive 16. What's the square root of 16? Plus and minus 4. So there would be a point at negative 2, positive 4, and there's also going to be a point at negative 2, negative 4. That's what gives us that parabola shape, is when you take a square root, you end up with a plus or a minus. And that's kind of true with both up and down and right and left, because it works both ways. Does that make sense? So, but that's also why there's no points over here.
So what if the vertex isn't positive?
Oh, we'll get there. I'm 2 weeks away from moving the vertex on you. I don't want to get into that stuff yet. I will get there, and it's actually really easy, but baby steps. Okay? Easy enough so far? Okay, here's how easy this is. Everybody take a look at page 623. 623. Huh? Oh, 623. Okay, on 623, and we're in the green book now, not the orange book, right? So, number 3 says y squared equals 16x. I can look at that right now and know the direction of this parabola. Is this going to go up, down, right, or left? It's going to go right. How'd you know it was right? Y squared tells me it's right or left. How'd you know it was right and not left? That's a positive. So all I'm going to do is say 4p has to equal 16. So my p value is going to be 4. So I go right 1, 2, 3, 4, left 1, 2, 3, 4. I'm going to have a focus point over here at 4, 0. I'm going to have a directrix line back here at, would it be x equals or y equals? X equals negative 4. And this would be a fairly fat parabola going to the left. It really is that easy. Like, there's nothing to do. What's the only thing you'd have to do to a question like 22? What's wrong with 22 where it says negative 5x plus 1/3 y squared equals 0? What's wrong with this right now? It's not in standard form. What do I have to solve in order to get it in standard form? Whichever variable is squared. I need to get this to y squared. So I would add the 5x to the other side, multiply by the reciprocal, so I'd get what? 15x. So 4p is going to equal 15. It's just an uglier number. 15/4, or 3.75-ish. Right? And this is going to go which direction? Y squared, which means right or left, and then it's positive. So my focus point's going to be over here at 15/4, 0. My directrix line is going to be back here at x equals negative 15/4. And would this be fat or skinny? Or medium? This would be pretty fat going to the right. All there is. Simple enough? Look at number 26. Now they tell us where the focus point is. The focus point is at 2, 0. Our job is to write the equation. The hardest part of this is, where is that point? Up, down, right, or left? That points to the right. If it's to the right, which standard equation am I going to use? I'm going to say y squared equals 4px. What do you think my p value is in this case? What's the distance I went over? 2. So the answer is y squared equals 8x. Make sense? If you do a question like number 27, it's, well, let's do 29. It says 0, negative 4. Where is the point 0, negative 4? Down. That means my parabola has to be going down, which means I would use, was it x squared or y squared? X squared equals 4py. What do you think my p value is in this case? Negative 4. So the answer is x squared equals negative 16y. Simple? What? Why am I switching the x's and the y's? It's all dependent on what?
Well, when you're going left and right, sometimes that.
Parabola, here's one thing I'm going to say a lot in this chapter. Parabolas are the weird ones. Parabolas are the weird ones where when x is squared, it goes up or down. If y is squared, it's left or right. Just remember, parabolas are the weird ones. Okay? Okay, now it's going to get hard. Turn the page. I know. Now it's getting hard. Now they said the directrix line, if you look at number 39, is that x equals 3. Where is the line x equal 3? Well, I would go to the right 3 and draw a vertical line. What does that mean about my parabola? What direction should it be going? To the left. Which means, which equation should I use? Y squared or x squared? Y squared, 4px. What's my p value here? Why negative 3? Because we're going left. So the answer to this question is y squared equals negative 12x. Guys, parabolas are easy. They really are. There's not much to them. You're basically multiplying by 4 or dividing by 4. That's the whole problem. Why is it 4? It's because of the standard equation. The standard equation is y squared equals 4px. Easy enough? That's all there is. Okay.